So today we will discuss about the Saytzeff elimination versus Hofmann elimination in details. So in case of E2 elimination, there are generally these two choices. The mechanism will go either via the Saytzeff pathway or via Hofmann pathway. So what factors are essentially the cause for this anomaly? So today we will discuss that topic in detail. Okay, so this is the substrate which I have chosen for as an example to illustrate the mechanisms. In case of Saytzeff elimination, the leaving group must be a bromine or tosylate, iodine, etc. And in case of Hofmann elimination, the leaving group must be a charged leaving group, that is a quaternary ammonium salt type substrate or SME2. And an interesting case is when the leaving group is fluorine. So as we know, this substrate is displayed in this form, so where we can clearly see the different types of beta hydrogens. So in this substrate there are three types of beta hydrogens, and as we can see, the base can interact with all these three beta hydrogens seamlessly to afford these three types of alkenes. But you all know only one type of alkene will be formed. So what should be the alkene? So let's consider the acidity of these three beta hydrogens. So which one will be more acidic? So as you know, the beta hydrogen which will be attached with the less substituted carbon atom will be more acidic. This one will be highest in acidity. And the second one will be this, and the least acidic one will be this hydrogen. Why this is so? Because there are two methyl groups which have plus I effect, and essentially the electron donating effect will decrease the acidity of this hydrogen. There is only one methyl group, and in this case there is no methyl group. So the base will obviously try to interact or abstract this beta hydrogen, but the experimental fact, or rather evidence, clearly shows us that only this beta hydrogen will be abstracted. That is, this alkene will be formed, not this one, not this one. What is essentially the cause for this anomaly? The base should interact with the highest acidic hydrogen atom, but the least acidic hydrogen atom is abstracted by the base. To understand this, we have to consider so let us see the case of Hofmann elimination, and then we will go into the mechanism. So in case of Hofmann elimination, you can see here the same substrate, but the leaving group is different, NMe3 plus in place of bromine. So in this case also the acidity pattern will be the same. This hydrogen will be most acidic, and the least acidic will be this hydrogen. So and the base will accordingly react with the hydrogen, the most acidic hydrogen atom. In this case, the experimental facts suggest that our prediction is correct, and this hydrogen atom is abstracted by the base to afford this product will not be formed, and also this will be not formed. So in this case our prediction matches with the experimental fact. So why our prediction failed for Saytzeff elimination? According to the acidity of the beta hydrogens, the product will be this alkene, but it is not the case. This alkene is formed. So what is essentially the cause? And also it is a fact, we have to remember that in case of Saytzeff elimination the base is sodium ethoxide, and in case of Hofmann elimination the base we have chosen is sodium tertiary butoxide. So let's consider the transition states, or rather the mechanism of these two reactions. So according to the reaction, the mechanism will be the base will abstract this hydrogen atom, this beta hydrogen atom, and then this carbon hydrogen bond will break, the double bond will develop to form, and this carbon bromine bond or carbon leaving group bond will break. So the transition state looks like this. This bond is developing, or rather trying to form, this bond is trying to break, the double bond is trying to form, and this carbon bromine bond is trying to break. So we can clearly see that in this case a partial double bond character is developing in the transition state. So as we all know that any double bond which has more substituents, or any alkene molecules which are more substituted by the alkyl groups are more stable. So why they are more stable? The essential factor is hyperconjugation, as you all know. The carbon hydrogen bond will essentially go for the hyperconjugation process, and we can also explain this via MO diagram. This is the antibonding orbital of this double bond, and this will be the carbon hydrogen bond, sigma bond, or bonding orbital. This is, and this is the antibonding. So the interaction will produce two MO. The carbon hydrogen bond is filled. The new MO now contains the pair of electron in lower energy state. So that's why the system will get stabilized. So this is the fundamentals of the hyperconjugation process involved in stabilizing a double bond. So this concept, this hyperconjugation phenomena, will also apply in this case to stabilize the transition state. So the transition state will be stabilized by this hydrogen atoms, hyperconjugable hydrogen atoms. So as the transition state involves the formation of a partial double bond, the double bond will be formed in the position in which there will be maximum stabilization via hyperconjugation. So this is the most stable position for the double bond to form, and accordingly this product will be formed. So this is the case for Saytzeff elimination. And now if we consider the Hofmann elimination transition state or mechanism, so in this case the base will abstract the more acidic hydrogen atom, which is this hydrogen, obviously. But we have to understand that in this case the carbon leaving group, or rather the carbon nitrogen bond breaking, does not involve in the transition state. Why this is so? because the nitrogen here is positively charged, but in case of Saytzeff elimination there is a bromine atom which is electronegative element, but its electronegativity is not as high as this nitrogen which is positively charged. So obviously this carbon nitrogen bond is much more stable than this one. So the carbon nitrogen bond will not break in the TS, and also the minus I effect of this nitrogen atom will stabilize this developing negative charge which will be formed via the breaking of this carbon hydrogen bond assisted by the base. So the developing negative charge in the beta position will be stabilized by this group also. So these are the 2 points which you have to remember. And this will be the alkene in case of Hofmann elimination. So look carefully that this transition state resembles to U1Cb type, right, in which the carbon hydrogen bond first breaks to form a conjugate base and then the elimination takes place. So this is like a U1Cb type mechanism in case of Hofmann elimination. But in case of Saytzeff elimination, you can see that the carbon bromine bond breaking takes place in the transition state. As a result, in this carbon there will be a del positive character in the initial step of formation of a carbocation, and as soon as this del plus charge will develop in this carbon, the molecule will adjust itself to eliminate the suitable beta hydrogen atom in order to generate the mode substituted double bond. So this is much more like E1 pathway, right? So in case of Saytzeff elimination, the mechanism is like the E1 pathway. Now let us consider the factors affecting this anomaly. First of all, we have to consider the nature of the leaving group. Obviously, when the leaving group is uncharged, that is bromine, iodine, any halogen except fluorine, or OTS, OMS, mesylate, tosylate, brosylate, in that cases the favorable mechanism will be the Saytzeff pathway. And when there is a charged or highly electronegative element is present as a leaving group, like fluorine, SME2, NMe3+, in those cases the mechanism will be essentially Hofmann pathway. So that is the number 1 factor. Number 2 factor is the impact of the leaving group on the transition state. So as you can see, in this case the leaving group is capable of dissociating in the transition state, and therefore the mechanism shifts towards the E1 end of the spectrum, of the elimination spectrum. But in this case the leaving group is not capable of dissociating in the transition state, and the mechanism shifts towards the E1Cb end of the elimination reaction spectrum. So the impact of the leaving group is much more important in case of elimination reaction to decide whether it will be Hofmann elimination or Saytzeff elimination. Number 3 is size of the leaving group. This is very interesting point or factor. So to understand the effect of the size of the leaving group, we have to draw the molecule in Sawhorse projection or Newman projection. In this case I have drawn the structure in Sawhorse projection. So this is the Sawhorse projection formula of this molecule. Sorry, of this molecule. Okay. So as you know, for E2 elimination, the syn antiperiplanar condition must be maintained. That is, the hydrogen, this carbon and this nitrogen will lie on the same plane and must be anti with respect to each other. So this is the suitable conformation for E2 elimination. So now we have to consider whether this is stable form or not. As you can see, this is the number 1. If we number this carbon as 1, this carbon will be 2 and the nitrogen atom will be 3. So there will be a 1,3 syn diaxial interaction. This interaction is 1,3 syn diaxial interaction. So what is 1,3 syn diaxial interaction? As you know, in cyclohexane molecules, if there are two axial substituents, in this case two methyl groups, then there is a severe steric repulsion which is called 1,3 syn diaxial interaction, and this is not the case of gauche-butane interaction. In many online resources you may have read the interaction as the gauche-butane interaction, but this is not a gauche-butane interaction. This is clearly a 1,3 syn diaxial interaction. Okay, you can also draw the molecule like this. So 1,3 syn diaxial interaction between this methyl group and this 2 methyl group takes place when the molecule remains in this conformation. And the molecule, okay, so in this case the hydrogen is the least acidic hydrogen. We are now considering the steric attribute, so let's forget about the acidity of the hydrogen. So this is a possibility, that is a possibility. So in this case we can see that it is very unlikely because of the 1,3 syn diaxial interaction. So now consider this possibility. So in this case we can see that the base is abstracting the more acidic hydrogen atom. So now consider it from the viewpoint of steric repulsion. So as you can see, in this case there are no methyl groups, so 1,3 syn diaxial interaction is completely absent in this case. So as a result, this conformation is very much suitable, or the most suitable, for the substrates which have these large leaving groups like NMe3+ or SMe2+. Okay, so as the size of the leaving group gets increased, the mode of the E2 elimination pathway changes from Saytzeff to Hoffman. Let us consider the fourth factor, which is the size of the base. This is another interesting factor. Okay, let's consider the base is tertiary butoxide, which is the extreme condition where the steric repulsion will be maximum because of the presence of these 3 methyl groups. So in case of tertiary butoxide, the base should be approached from the exact opposite, or rather 180 degree angle according to this, with respect to this carbon hydrogen bond. Why so? Because the bonding interaction will be maximum when the two bond forming atoms approaches each other towards each other via head-on collision or end-on overlap. So the base will approach like this. So now it seems that there will be no such steric repulsion between these methyl groups and these methyl groups or that methyl groups, because they are so much further apart. So why the base size of the base impacts the reaction pathway? Okay, let's draw this structure in a different way. Okay, so this is the projection of exactly this interaction, or this tertiary butoxide and this molecule. Both these are same. So in this case you can see that the oxygen, hydrogen and these two carbon atoms will lie in a single line, and rest of the groups will lie like this. These three methyl groups will be situated like this. So now if we draw the Newman projection formula in order to better understand the steric factors, this will look like that. If we see from this side, the two methyl groups will be in the top, this methyl group will be at the bottom, these two methyl groups will be in the bottom, and this big group will be in the top. So we can see that there are two Gauss-Butane like interaction, and also there are also extra two repulsions which are Gauss-Butane like, but not exactly, obviously not the Gauss-Butane interaction, but a slight repulsion will take place between these groups. Slight, but the repulsion will exist. But if the tertiary butoxide now abstracts either from this methyl or this methyl groups, then the situation will be like this. Now the two methyl groups will be replaced by these two hydrogen atoms, and this will be the case. So this will be the projection of the same interaction. So in this case we can see that the previous methyl repulsions are now gone for this case, but these repulsions are still there. So if we compare these two situations in which this transition state looks like sterically more crowded than this transition state, obviously there are no repulsion in these two cases, in these two position, but in these two position there are steric interaction. This steric interaction and that steric interaction is also similar to these two. So this situation favors most for large base like tertiary butoxide and also this base. Okay, so these are the four important factors which you will have to consider to determine whether a reaction will go via Saytzeff elimination pathway or Hofmann elimination pathway. So that's it.